Welcome to another practice VHDL, and today we're going to practice to write the code the code in VHDL, implementing this circuit. It's a free running binary counter which will be running from 000, it's 4-bit, which is 4-bit. It will be running from 000, going to 001, 0010, like that, and then it is also going to wrap around such that when it reaches a maximum, it comes back again to 000. We are also going to have a max pulse here, which is basically going to tell us when we reach 111. And we're going to utilize a few components. We're going to utilize a D flip-flop, a positive edge D flip-flop, which in this case is going to be our register, and we're also going to utilize a max to get our max pulse when we reach 111. All right, so just a quick recap on how our D flip-flop works. So we'll be utilizing a D flip-flop with reset, our asynchronous reset, which means that we don't have to wait for a clock to do our reset, or we don't have to wait for rising edge when we have our reset. So when we have our reset, nothing else matters. Our next state is going to be 0. Our next state in this case is our register. And then since we have our flip-flop is a positive edge, we are going to have it, it doesn't matter whether the clock is 0, our next state will remain the same, or when the clock is 1, the next state will still remain the same. And when we have a rising edge, this is when we have our next state now changing to, our current state changing to our next state. So let's get right to it. What I usually like to do is go where I'll be writing my code and make a folder. So this folder, we're going to say that, let's call it binary counter. All right, so after we make a folder, then open your IDE, whichever you're using. For me, I'm using Visual Studio. Then open your folder, and then go to binary counter. So when you after opening it now, we make our file here. Let's call it so let's just call it binary counter as well. Binary counter .vht. So we're making a VHDL file. Alright, so the first thing to do is we need to import our library, our IEEE library. Then import other libraries. So we use the numeric library. Well, I also like to use this library, this std library. Okay. And now we describe our entity. So what I usually like to do is, first of all, just write the entire uh, layout of the VHDL code, then just start filling up. After describing our entity, now we write our architecture. All right. So now that we have the layout of our VHDL code, let's go back to check out our circuit. Okay. So we need now to put our ports here. And if you look at our circuit, we have the inputs and outputs to our circuits. We have the clock and the reset as our input, and we have the max pulse and the Q as our output. So we're just going to describe those ones in the port. So we say that we have a clock and reset as the inputs. So clock is an input, it's an STD logic, and then we say that we also have our reset, which is an input as well, and it's an STD logic. And then we say we have a max pulse, which is an input. Sorry, this is an output. It's an STD logic as well. And then we have Q. And if we look at Q, since this is a 4-bit register, it means that our Q is going to be 4 bits. Alright? Okay. So we say that Q is an out, STD logic, this time it's a vector, and it's 4 bits, so it's 3 down to 0. Alright, so let's save that. Okay, so coming back here, looking at the circuit, we also see that we have a couple of wires. We have this one, and then we have this one. So this single wire here is this one that goes to Q, this one that goes to our max as well, and then we have the same wire again going back to our incrementer here. So we basically have 2 wires, and in VHDL, how do we describe our wires? We describe them using signals. So it means we need to have 2 signals. So we describe signals right here. Okay, so we have 2 signals. We say signal. So this basically describes the current state of our register, sorry, the current state, yes, the current state of our register or our circuit. And this one describes the next state of our circuit, which is determined by this logic right here. So our signals is going to be our register, which is our current state of the circuit, and then we also have our next, which is a next state of the register. So we have our register, which is a current state, and then we have our next, which is the next state. All right, but for these ones we are going to describe them. They're also 3 bits because of our output, and we said that our counter, our register here is a 4-bit register. So then because we have this addition right here in VHDL, what we do is we're going to have an incrementer, so we need to describe this as unsigned so that we'll be able to add them to add 1 to this bits when they are unsigned bits. Okay, so we say that this is going to be unsigned. Unsigned, right? Unsigned number 3 down to 0. Okay, so what we do now, this circuit is basically actually divided into 3 parts. We have our register right here, and then we have our next state logic. Our next state logic is this one. This is our next state logic, which simply determines the next state of the registers or the circuit. And then we have our output logic, which is this output logic right here, including this P as well. So what you want to do is you want to divide your circuit into those 3 parts. So you have your register, and then you have your next state logic, and then you have your output logic. All right, so let's do our register. For us to do this register, which is a 4-bit register, we actually say that our register only wakes up when we have a positive edge from the clock and when we have reset. So we have to make a process here with the sensitivity, where the sensitivity list is actually just the clock and the register. All right, so in this case, to make our process, we say process, and then we put our sensitivity list here, which is going to be clock, and our reset. Perfect. So we said that for our register, this reset is asynchronous, which means that it doesn't have to wait for the clock. Whenever this one goes 1, the output of our register goes to 0. So what do? We have to check, first of all, if our reset is actually equal to 1, or is 1 is on. So if it's equal to 1, then we say, well, let's just write this. Okay, if it's equal to 1, then what do we say? We say that our rnext, not rnext, but our r register, this one here, this is our signal now, which is our output, which is our y actually, but it's a signal. So we say our r register gets 0 0, basically get reset. And how do we do that in VHDL? Instead of writing well, you can also write 0 0 0. Alright, but good practice states that you want to write, this is how you make sure that all the other signal goes to 0. I mean, you have a 0 0 0, because you will never know if you want to change the size of your inputs. Alright, this then will make sure that everything goes to 0, that we have a 4-bit 4-bit zeros here. Alright, so else if we also need to check if we have a rising edge. In this case, this is not 1, which means reset is not on. So then let's check if we have a rising edge, which is the only time our state will change. So we say we need to check for a rising edge. Rising edge of the clock. If we have that, then what happens? If we have a rising edge, then now we can update our current state to the next state. So we say that our current state then becomes our next state become our current state. Perfect. Then we say and if. Alright, so we've taken care of our register. Now we need to take care of our next state logic. Our next state logic is this one, which is simply incrementing the current state, incrementing the current output to get the current state, the next state. So this one says that the next state equals to current state plus 1. So we simply say that our next state is the current state which is our register plus 1. And in VHDL it's very good that when we get to 1111 here, then we add another 1. It will wrap around and it will actually take us back to 0 0 0. Okay, so we don't really have to do any more computation here because this will automatically just go back from 111 to 0 0 0. All right, so we took care of the next state logic. Now let's take care of the output logic. So in the output logic we say that this register, the current state goes to output, which is Q, and we also have to check if we have 111 so that we can have a pass here, right? Right, so what we do first, let's first of all say that our queue gets our current state, which is our output. And before that, you need to know that, okay, well, let's say, let me write this down first of all. Gets our R register, which is the current state of our register. All right, clearly shows here that this one now goes to our output. However, you can see that we defined here our R register as an unsigned binary, but our Q here, which is our output, is an STD logic. So this will definitely give us an error if we run it like this. So in order to change this to a binary, to an STD logic vector, we simply wrap it inside this STD logic vector. So we simply say STD logic vector. All right, perfect. So we've taken care of this one. Now we need to take care of this one. So how do we take care of this one? So it's a max. We have a max. We have a max here, which is a 2 to 1 max. All right, and we either have a 1 or a 0. And we say that our max pulse, let's say that our max pulse does what? Our max pulse simply takes in, becomes our max pulse. We're using this as our select signal. We will be selecting a 0 or a 1 to get our max pulse. So we say that we will select a 1 when our R register is equal to 1111, else select a 0. So what did we say there? See, we look at our R register, yes, which is our current register here. So we say that we select a 1 only when we have this one, only when our R register is equal to 111. Then we select one. Any other time apart from that, we will be selecting a 0. So every time we reach 111 in our output, we will be able to see a pulse here. All right, so having done that, we have completed this we have completed the code. Now let's see how we're going to run it. Now I'm using Model Sim to run my simulation. So if you're using the same thing, just go to Model Sim. Now you can create a new, go to new, then you say project, and then you locate where you made where your project is. In my case, it's right here. Will be your project location. And then you say that the name of our project was, this name should be the same as this one, so it's binary counter. Okay, so we say it's binary counter. Okay, so this is the name of our project. Actually, you don't have to name the project here. Well, actually you don't have to, you do have to name the project. So binary counter. All right, and then say okay. And then this small pop-up will appear. Then say add existing file, and you will be able to get, this is a VHDL file that we just created right now. So in order to compile it, you have to select it, open it. Oh, okay. Say close. So now we compile it. So select it, compile, and it seems we have one error. Let me just expand this. So let's see what the error is. The error says that it's in second line. In the second line, so let's see. The second line, we're saying, oh, okay, so we have a double full stop there, double dot. So okay, I changed it, save it, then come back here. You see, we still have one error. I am saying in line 20, the 0 is not type of IEEE. All right, so let's see, what is it? Let's go to line 20. Line 20. Okay, here. So this one is supposed to be in single quotes. All right, supposed to be in single quotes. We save it, go back, let's check it out. All right, so you see now here we have our successful, that the compilation was successful. So how then do we test this? Okay, let's go back to our project. All right, so we said that when we start our clock, when we simply need to have our clock running, because it's a free running clock, it's a free running counter, so it's a free running binary counter. So we just, when we run our clock, it will automatically run from 00 every time we have a a rising edge. It will automatically run from 00001 all the way to 111 and then drops around. So what we just need to do is we need to have this functionality of this clock running this first. So we need to find a way of running our clock. Okay, so we say let's simulate it now. The easiest thing would be to write a test bench, but I feel like that will take a bit more time. Let's see how much already do we have. It's already 28 minutes. So okay, right, let's do it. Let's see, simulate. We go to simulate, start simulation, and then work binary counter. Okay, so then you have this. All right, simulate. Okay, usually have this problem. I don't know why it keeps on doing that. So select wave, then we select our inputs. So we have clock, reset, max pulse is our output. All these other ones are okay, and Q, and this one and this one's our internal signal. Okay, if you want to analyze all of it, just select and then go to click, hold shift, and then get them here. For it to look nice, just click this one, toggle leaf name, then you'll be able to see all of it nicely here. All right, So after we get this, now let's test to see what we are getting. So let's have a running clock. Let's change this to clock, and let's just have it, the VHDL is measuring it in picoseconds, like up here. So let's have a period of 100 picoseconds, which is fine. All right, and let's also make sure that we have our reset. We must first of all reset our circuit to be 00 before it starts running, because our next state will be undefined, then undefined plus 1. So therefore, if we don't start with a reset, then we won't have a 00 here, because right now it's just undefined. Right, so to do that, we click reset, and then we say false. We say let's have a 1, which is reset, and then this delay for simply means for how long do you want to delay from before you set this one. So let's just say let's set it right away. Okay, but then we don't want it to stay 1 for forever, because when it stays 1 forever, it means our circuit will be reset forever. So let's then select the same reset and then false, because we know our clock our period is 100 picosecond. So let's say that let's have a value for reset, let's have a value of 0 after we delay it for the first 100 picoseconds, which is equal to 1 period of our clock that we selected. Right, and then let's say okay for this one. So let me just create some room here before we run, so that we'll be able to observe what happens clearly. All right, so 100 picoseconds, this will only give us, okay, if we're running our entire simulation for 1000, this will, and we have 100 picoseconds per clock cycle. This means that we only have 10 next states. Our system will go through 10 states, but it will not be enough for us to observe all the states, which are supposed to be around 16. So let's just give it 2000 to be a bit better, so that we have around 20 next states, which will even help us to see the next the wraparound that we've been planning. So after setting that, now we click run and see what happens. So we click run. All right, so we see that our clock is running well. We see our reset is definitely 0. So let's zoom this out and then observe. So we can see that we start with 0 0. We go to, this is Q, by the way, this is the output. These are the signals. We don't really have to observe these ones for now, because they are really internal. So this is our output, and this is our output as well. So we can clearly see that there is our pulse here. But before that, we can also observe that we have 0 0 1. We start with 0 0 as our output. We go to 0 0 1, 0 1 0, 0 0 1 1. 0. So it definitely is counting up until we get to 1101, and then we get to 0 to 111, at which point we have a pulse, which is a pulse telling us that okay, we've reached the maximum, 111, and then it drops around, starts from 00 again. So far it looks like the circuit is running quite well, just the way we programmed it to run. It's going to start from 000, continue counting up until 111, and then it drops around. So that's it for me. I hope this is good practice for you for programming in VHDL. See you in the next practice. Thank you.